Okay, so welcome back everyone. So in this video, we'll be looking at a worked out solution for creating a DFA M that accepts the language L, where L is a set of all strings over 0, 1, such that these strings have 3 zeros, so exactly 3 zeros, and at least 2 ones. Okay, so in other words, if I rewrite this with a more sort of formal representation. So if I let n0 define, so let's see here. If I let n0 of w and n1 of w define the number of zeros in w, and then similarly for, right, so this just means I'm copying over what's the line above. So then I can just rewrite this as w in 0, 1 star, such that the number of zeros in w is exactly 3, and the number of ones in w is at least 2. Okay, so what's the idea here? Well, this is a bit similar to, let's say, I want like an even number of zeros and an odd number of ones, right? Except that in that the role of my state is twofold, right? It's tracking the number of zeros and the number of ones, right? But it's different because now I'm not tracking the parity, I'm actually tracking the count, okay? So I think one good way of illustrating the start to a solution would be if I created a table. So let's say I created a table, a two-dimensional table, where I encoded the number of zeros. Let's write this like this. So if I had the number of zeros and the number of ones, right, written like this. So I want exactly 3 zeros. So if I have 0, 1, or 2 zeros, then I'm not happy. If I have 3 zeros, I'm happy. And if I have more than 3 zeros, I'm back to being sad, right? So these are all sad, right? Okay, so this is actually the only column I really care about for the number of zeros. Like, that's really the column that's going to determine whether or not I have the correct amount of zeros. And then for the number of ones, I can have 0 ones, I can have 1 1, or I could have at least 2 ones, right? So in this case, I'm sad, in this case, I'm sad, and in this case, I'm happy. So really, what I care about is really the intersection of these two guys, right? So what entry in my table am I happy, right? Am I happy in this column and in this row? Well, that's going to be this guy and this guy, right? So it's going to be the intersect of the happiness. It's going to be here, right? So I'm going to be happy here and only here, really. Because if I happen to have more zeros, then that's no good. That's not going to be my language. If I happen to have less zeros, then that's no good, right? So that goes for any number of ones, right? So it doesn't matter what my number of ones are. If I have less than 3 zeros or more than 3 zeros, I'm not happy. And then if I have exactly 3 zeros, but I have less than 2 ones, so I have 1 1 or 0 ones, then again, that's not good for me, right? So actually, the language is really encoding this kind of idea, this property. So all that's left to do really is to take this idea and just convert it to a state diagram. And that's actually not that hard, right? Because I said that my states need to encode 2 simultaneous rows, role of tracking the number of ones and the number of zeros. So what I can simply do is make each of these guys states, right? So I make each of these guys states. Okay. I know that my start state is going to be here. Then I'm going to, if I have more ones, I transition this way. And if I have more zeros, I transition this way. And where do I accept, right? Where do I accept? Well, the only place I'm going to accept is here. So what does this look like, right? What is this actually going to look like? Whoops. So let's actually write a proper DFA. So again, remember, I care about number of zeros. Is that number of zeros? Yes. Number of zeros being 3, and the number of ones being greater or equal to 2. So you can think of this as one axis, right? So in this one axis here, I'm encoding the number of zeros, and then in this axis here, I'm encoding the number of ones, right? So here is my transition for zeros, right? So here I have 3 zeros. If I have more than that, then I'm just going to reject, right? And then my other axis is for the ones, right? So if I have 1, 1, if I have 2 ones, then now I'm happy. And then if I have more than 2 ones, right, then that's not good. Then I'm going to be rejecting that. Or no, actually, I'm not, right? Because what I care about is, sorry, I just made a mistake there. I care about at least 2 ones, right? So whatever comes after, I'm happy, right? I just stay at this state because I know that I have at least 2 ones, so I can just stay there. And then the idea is just to combine these 2 states together by sort of joining the axes, right? So that means that if I have a single one, but then I read some zeros, then I go along this way, right? And then it doesn't matter, right? So if I'm here, it doesn't matter if I see more ones or zeros. I already know that it's an automatic reject because I have more zeros than I want, right? And the same thing for this guy. Right? And again here, if I, in my vertical dimension, right, if, let's say, I see some zeros and then I see a 1, then that means that I have 2 zeros and a single 1. So if I get another one, then I'm at least 2. So that's one condition for happiness. And then if I get another 0, then I have exactly 3 zeros, and that's where I want to be at, right? So that's how I encode my other transition. So vertically, I go this way. And then horizontally is for my zeros, right? And so the only place that I actually care about, the only place in this field that I really care about is this guy, right? Because in this guy, I know that I have at least 2 ones, and I have exactly 3 zeros, right? Because this is actually encoding all possible paths, all possible ways to get 3 zeros. I can either get 0, 0, 0, and then just a bunch of ones, or I can have maybe a first 0, then a 1, then another 0, then a 1, and then another 0. So then I have 3 zeros, and I have at least 2 ones. So then this will be my only accept state. And then together, this machine altogether is the machine that accepts the language L. So one thing that I want to mention, but I'm not going to go through the whole process of recreating a machine, is there's this other nifty property of DFAs. So suppose I have 2 DFAs. So I have DFA M1, which is Q1. Let's close this. Which is Q1. Let's say it's the same alphabet. Whoops. How am I going to denote? Let's say delta 1, Q0, superscript 1, and then F1. So that's one machine. So the language accepted by this machine is L of M1. And the language accepted by M2, then I have another machine with states Q2, the same alphabet, the transition function delta 2, initial state Q0, superscript 2, and final state F2. So then this language accepts L of M2. So there's this nifty property of DFAs that allows you to create a machine. So you can create a machine M such that the language accepted by M is the intersection of M1 and M2. Okay? So how do you do this? Right? How do you create a machine that accepts the intersection? Okay. And this is related to our problem because if you'll notice, there's an intersection here, right? I care about 3 zeros and at least 2 ones, right? So how do I do this? Well, what I say essentially is I say that in my create a machine M, I'm going to create a state, and this state is going to encode information from M1 and information from M2. And the way to do this is to make states represent tuples, right? Where the tuple is going to be an element from the cross product of Q1 and Q2. So a state in my machine M is going to be a tuple of states, right? So in my machine M, let's say M is Q prime, sigma, delta prime, Q0 prime, and then F prime, right? So my set of states is going to be the cross product of Q1 and Q2. Okay. So why, right? So the intuition is that I want my states in my machine M to think of both what they would be doing in M1 and in M2. Okay. Right. And the only way that you can accept a string in M, right, in the machine of the intersection, is if you're in a final state for both M1 and M2. Okay. So actually the set of final states in my machine M prime is going to be F1 cross F2, right? And so actually you'll notice that this implies that if, say, F1 was empty, right, then F prime would automatically be empty, right? And that's the behavior that you expect, right? If it's impossible, if no string is accepted by M1, then the intersection of the language accepted by M1 and M2 should also be empty, right? So this satisfies our intuition. And then what should be Q0 prime? Well, Q0 prime, I'm going to say, is the start state for both M1 and M2. It's going to be the start state for M1 and M2, okay? So that if I have two machines, right, so I have my machine M1 and I have my machine M2, then my machine M prime here, the start state is going to be labeled as, or it's going to encode the role of Q01 and Q02, right? And now, right, what do my transitions look like? So this is the most important thing, right? So what do my transitions look like in this space? So delta prime now, what it's going to take is, well, delta prime always takes a state, right, and a symbol. It's just that now a state for me is a tuple of states of the original machines, right? So let's say it's state S1 and S2. So I know that S1 is in Q1, and I know that S2 is in Q2. So what happens if I read some letter A? So suppose A is in sigma, right? What can happen, right? So the state that I need to go to is the state that I go to when I read A from S1 and the state that I go to when I read A from S2, right? In the respective machines of M1 and M2. So what does this look like, right? Remember the output of delta prime, which is just a transition function, this should be a state, right? But this is now a state in M prime, right? And states in M prime are actually tuples, right? So the state should be an element of Q1 cross Q2. So then I write a tuple, right? So a tuple, a two-pair tuple, where the first element of my tuple is actually the state I'd be in if I was in S1 in my machine M1 reading A. So you'll notice that I'm going to use the transition function of M1 here. So delta 1, right? So this is the transition function here, right? And, right, so I'm going to be in that state, and at the same time, I'm going to be in the state delta 2, right, where, I'm going to be in the state that I would be in if I were doing the computation in M2, reading the symbol A at the state S2. Okay, so you'll notice again that I'm using the transition function of my machine M2, right? So what this is doing, right, the idea is that this encodes the intersection of the computation of M1 and M2, right? So then if I read a 0, then I'm going to be at the place I would be in M1 if I read a 0, and the place I would be in M2 if I were to read a 0. And then the same thing for 1, right? Okay. And so this isn't, right, this is how you would construct a machine. I'm going to omit the proof that actually proves correctness. But this is all to say that what you could have also done for this problem, although it might have been a bit more work, is you could have created a machine for the language 0, 1 star such that W has 3 zeros. And you could have created another machine over 0, 1, the alphabet 0, 1, that accepts strings with at least 2 1s. And then you could have combined these two machines using this procedure, right? This would have just been a lot more work, well, I think, because then you would have had the number of states in M prime, right? So the number of states in M prime would be the number of states in M1 times the number of states in M2. And in this case, in this case here, I'm actually potentially reducing the total number of states, right? Because, or maybe not actually, because here I have 4 states, 1, 2, 5 states, sorry. And then here I have 3 states. So I might have gotten 15 states anyways if I had followed this procedure. But I think the main idea actually of this property is that, so what's the implication really? If I add another page, right? So what's the implication? Well, the implication is that if, right, so implication is that if L1 is regular and L2 is regular, right, what does this imply? This implies that there exists a DFA M1 such that the language accepted by M1 is L1, and there exists a DFA M2 such that the language accepted by M2 is L2, right? So if L1 and L2 are regular, then L1 intersect L2 is also regular, right? Why? Well, because from this property here, I've shown that from M1 and M2, I can construct a machine M prime that accepts the intersection. So, right, because I can construct M prime, right, which is still going to be a DFA, and this DFA will accept L1 intersect L2, right, because L1 is the language accepted by M1, and L2 is the language accepted by M2. Okay, and so this gives you a closure property of regular languages that the intersection of regular languages is also regular. Okay, so that does it for this video, which first gives you a solution of the exercise and actually gives you an extra tidbit about the intersection of regular languages.